So now we are going to take the conversation of heat and apply that to heating curves because they show how energy changes through phase changes. So now I have water. I can talk about, okay, what happens as it goes from a solid to a gas. And I can do it for any type of matter. And we are going to do it in terms of heating curves. There is also this thing called cooling curves, but cooling curves are the opposite of heating curves. Heating curves are going up, cooling curves are going down. So if you know one, you know the other. So when we have a heating curve, let's say for water, water always starts as a solid. That we have to heat up that solid until it starts melting, and it's going to stay in the melting phase until all that solid is melted. Once all the solid is melted, we have a liquid, and that liquid is going to start heating up until it reaches the boiling point where it's going to start boiling. It's going to remain at the boiling point until all the liquid has boiled or evaporated, and then we get that gas phase. And then it's just a matter of heating that gas to a different temperature, which it might turn into a vapor. Okay, for water, the melting point of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. Those two values are known for water and for other substances. So if I give you a liquid that is not water and you're dealing with a heating curve, you need to know what the melting point and the boiling point are in order for you to construct this graph. As you are going up, because we are plotting heat versus temperature, as you're adding heat, the temperature is going up. It's like a staircase. And we are going to look at all those regions separately because the calculations of heat are done differently for each of those regions. Okay. You need to know how to read this graph because when we get to the problem at the end, you need to know what's going on to that substance because you're going to be told, okay, I have water that's being heated from this temperature to this temperature. How much heat is generated? So you need to know what phases is going through to know how to calculate those heats. And that's where we're heading towards. First, we are going to look at what is happening on those regions. Anywhere where the line is going up is because kinetic energy is happening, meaning the type of matter, or let's say in this case, water is being heated up and the temperature is changing. So kinetic energy is increasing in regions where the graph is going up. In regions where it's flat, there's no kinetic energy, there's only potential energy. So we can talk about potential versus kinetic in a heating curve. If it's going up, kinetic. If it's flat, potential. So right now you're seeing that there's 5 distinct sections in here. The first section is where we have a solid heating up, that's kinetic energy. Then melting, which is flat. Then we have the liquid heating up. Then we have the boiling point or evaporation section, and then it's just the gas heating up. So 1, 2, 3, 4, 5 regions. 3 of those have kinetic energy, only 2 have potential energy. So the heat is going to be calculated in 2 different ways. One way when it's going up, and another way when it's constant temperature. When it is going up, we are going to use the Q equals mc delta T because there's a change in temperature. These specific heat capacities, I told you need to know the one for water, but there's also one for ice, and there's also one for gas or steam. Depending on the type of problem, I will probably give you those values. So you don't have to worry too much. I only making you memorize the one for water. Again, anytime temperature is changing, we are going to use Q equals mc delta T. So how do we calculate the heat when the temperature is not changing? If I go too fast, let me know. So when the temperature is not changing, that's when it's boiling and when it's melting. In that case, temperature is constant. In here, we are breaking or making bonds. Well, actually, we're breaking bonds because we're heating. So we are not really making molecules move faster, which is what changing the temperature does. We are setting them free, we're separating them. So because of that, we need this thing called heat of fusion and heat of vaporization. That is the energy that is required to melt a solid or the energy required to evaporate a liquid. There are known values. I will give you those as well. So for when we are melting, we are going to use this equation called Q equals M delta H of fusion. The delta H of fusion is this value up here. The Q equation has nothing to do with temperature. It only deals with the amount of matter you have, the mass that you have. And then when you're evaporating, we call it Q of evaporation or Q evaporation. So that Q will be M delta H vap, which is also a known value. So temperature changing, I use Q equals MC delta T. When it is melting of evaporating, I use Q equals M delta H. That delta H has a different meaning of heat that we don't get to explore in this class. That's a Chem 1 topic. Okay, so now we know how to calculate the heat when temperature is changing, how to calculate heat when we are melting or evaporating, let's say water. How do we solve these problems? There's a series of steps. So the way I will do it is you have your heating curve, that's step number 1. Label your starting and end temperatures because that will tell you which regions of the heating curve you are dealing with. That is going to tell you if I am which sections I'm increasing temperature, which sections I am keeping the temperature constant. And then I'm going to calculate the heat for each one of those sections. Once I calculate the heat for each one of those sections. I'm going to add all the values together. And the overall heat is the sum of all the heats to go through the heating curve. The same applies to a cooling curve. The only difference is that the delta T's are going to be negative instead of positive. It's done the same way. So I have one example, and once I am done with that example, we are done with the notes today. Just holding up a little bit because I know some of you are writing. Let me just give it like a minute or two more, and then we'll move on to that sample. Remember, all the slides are always available in your Canvas, so you can always go back to them if you need be. And there's also the video of the class I always post after the class. Okay, so let's move on. So here's the challenge. I have 50 grams of water that goes from minus 25 to 130 degrees Celsius. How much heat is required to do that? I am giving you the heat of fusion of water and the heat of vaporization or boiling of water. So it goes from minus 25 to 130. So let's look at the heating curve. So the starting point is minus 20 degrees Celsius. So to get to 130, I had to take that solid from minus 20 to 0 because that's the melting point. Once all that solid is melted at 0, I have a liquid that I had to take all the way to 100 degrees Celsius. Once I get that liquid to 100 degrees Celsius, I have to evaporate all that liquid. Once all the liquid is evaporated, I have a gas at 100 degrees Celsius that I have to take to 130. So I have 1, 2, 3, 4, 5 sections that I have to calculate heats for. For 3 of those, I'm going to use the Q equals MC delta T because the temperature is changing. For the other 2, I am using the delta H G to calculate the heat because there's no temperature change. When it's flat, for melting and boiling, I'm going to use these 2 values in here. For the other ones, I'm going to use the C of 4.184. So when I heat the solid from minus 25 to 0, it's just the mass times, actually I'm going to use the C of the ice times the delta T. So it goes from 0 to 25, so from minus 25 to 0, I'm sorry. So the difference is 0 minus 25, so that change is positive. And the heat ends up being 791.25. That's step number 1. Step number 2 is melting. For melting, I use the Q equals G delta H of melting. So the mass still 15. The mass does not change throughout. The delta H is the H melting, which is 334. And that's how I get the 5,000 joules. And just a matter of adding those two heats for now for these two steps. While we wait for people to finish writing, those that are done can move on for step 3, 4, and 5 and start setting it up. Okay, so step 3 is the liquid from 0 to 100. Again, it's Q C delta T. Q is MC delta T. The M still 15. The C, because it's a liquid, is the C of the liquid, which is 4.18. And then the delta T is from 0 to 100, so it's going to be 100 degrees Celsius delta T. I can calculate the heat for that step as 6,270. One thing that I want to use this is as you go from the being heated to the liquid being heated to the gas being heated, the amount of energy increases. That C value is higher because it requires more energy to take the solid and turn it into liquid, and the liquid to turn it into a gas. As you move on in the heating curve, that heat increases because of that delta T is going to be bigger. It's a temperature climb. So once we have the third step, we just need step number 4 and step number 5. For step number 4 is the boiling. So M delta H of vaporization. So it's 15 times 2260. So I get a heat of 33,900 joules. And our last step is just taking that evaporated gas and heating it up to the final temperature. And that case is MC of vaporization delta T. Once I calculate all the heat for all the steps, the last thing we have to do is add all those values together. And the final answer is going to end up around 46.9 kilojoules. Would I give you a problem with all these steps? Possible. Considering it's going to be in the final? Most likely not. So how I will test you for this? I will give you information for one of the steps, but you need to be able to realize what that step is. If the temperature is changing, you're going to use Q equals MC delta T. If the temperature doesn't change, then you need the delta H value, either for melting or vaporization. So you'll have those values available. I will not tell you which one of the two you need to use. That's part of the problem. You're realizing which one you have to use and which part of the heating curve you are dealing with. Okay, so this example is the worst case scenario. Is the hardest you could have in this type of calculations at this level. Again, I don't have to ask you to do all the steps. I can answer you just one step, because if you can do one step, I'm going to assume you know what you're doing. Okay, so with that, we are done with heat.